Set up the draw mode. Give me some marker. Okay. Test, test, test. Oh, works great. Love it. Okay. We are going to do here a unit, what is it, 11 rotation test review for the CP class. And what we're going to start with here is the C1 problems. These problems are rotational kinematics problems. So equation 1R, and then maybe 2R, 3R, 4R, or 5R, okay, will be used in these kind of setups. The other thing we want to remember whenever we're doing these type of problems is to remember our linear to angular conversions. Those are on the back of the best friend. Stuff like omega equals V over R. Those are our conversions on the back. Those are the things I keep saying that everybody's going to forget, because even during our Beyblades lab, people forgot about them. They were asking where we could find these equations to do these conversions. So these are just rotational kinematics. And you're probably using equations 1R or equation 2R, 3R, 4R, or 5R on our new best friend. Something you need to be aware of is these equations here, 2, 3, 4, and 5. These are for accelerating motions. So if your object is spinning and then it speeds up or slows down, then you'll use these equations. So for our Beyblade lab, as soon as we ripped them, they started to slow down. They're just naturally going to slow down due to friction. So if you have an acceleration or an angular acceleration, then you'll use these. You'll use equation 1R whenever you have a constant motion. So let's just take a look of a made-up kind of C1 problem and what we can kind of look at here for this motion. Let's pretend, a ground ball is hit. So a baseball is hit along the ground, and it is making, let's see. Let's say the baseball is making 40 revolutions per second. And it rolls like this, hard hit ground ball. It rolls for this for 1.2 seconds. That's a time, clearly in seconds. These revolutions per second are actually an angular displacement, a theta value. And let's just say, a baseball is about yay big. It's about that big. Let's just say the radius of a baseball is somewhere along the lines of 5 centimeters. Give or take something, but 5 centimeters is a nice number, so that's 0.05 meters, okay? If we have something like this, something with an angular, excuse me, this isn't theta, this is omega. Whoops, that's omega, that's a revolutions per second. If we have something here with an angular velocity, a time, and some radius, we can calculate a few things. Let's, for part A, let's calculate omega, but let's put it in radians per second. Right now we've got this pesky unit of the revolution, and while it's nice you can think about things in RPMs or revolutions per second, it's not exactly a intuitive mathematical unit. So what we're going to do here is let's just convert this. We can say that 40 revolutions per second, and if you had something like RPMs, that'd be the same thing, revs per second. We've got revs per second. So we've got 40 revolutions per second, and if you wanted to train track this or dimensional analysis, fence post, whatever you like to call it, we know in one revolution or one go around of the unit circle, there are 2 pi radian, and that's in one revolution. So if I work this out, I see that my revolutions are going to divide out. I see I have radians per second, and it's nice to leave angular quantities in terms of pi. That's just a kind of mathematical thing we do because we like thinking about these pi values. So we're going to do 40 times 2 gives us 80 pi radian per second. And if you wanted to be like, oh, Mr. Botzer, I like to multiply those, you could just bust out your trusted calculator and just say, hey, 80 times pi, it's going to be around 240th, because I know 8 times 3 is 24. So you could also just call this 251 rad per second. Either or, you'd be fine. Okay, so that's part A right there, just a little unit conversion to put that into a better unit for us. For part B, let's figure out how far this baseball rolled. Now, I talked about this in class, but this word, these two words right here, how far, they are linear quantities. They're linear words, okay? So if someone's saying how far, this is linear, okay? So we need to be very, very, very careful about that. What we need to do here is we'll need to either convert our angular velocity into a linear velocity, or we'll need to get an angular displacement theta and convert that into a linear distance. However you like to do it, we just need to put things into linear velocities. And either way, if we kind of think about this, if we did this for rotational quantities or linear quantities, for the rotational quantities, how far theta is going to be equal to omega times t. For the linear quantities, how far x is going to be equal to the velocity times time. In either case, we still have some idea of what a velocity is, whether it be angular or linear, and we multiply by time. So if you wanted to, you could either do this first on the left here, you could do this and then convert this quantity here, or you could convert omega first into an angular velocity and then solve this out. It doesn't really matter which one you do. Either way, you would use the, if you want to do over here for omega, you could say that the velocity is omega times r. Over here, you could say x is equal to theta times r. Those are our conversions that we have, okay? Let's just kind of do this one on the right here. So if we know that the velocity equals omega times r, we know our velocity here is the angular velocity of 80 pi radians per second times a radius of 0.05 meters. When we multiply those together, since we're going back to linear, it's actually nice to multiply by that pi value. So 8 times pi was 251 times 0.05 is going to give us about 12.6 meters per second. Remember, this radian unit goes away. While radians are helpful for looking at a circle, they're not a physical quantity. You can't like measure a distance of radians. So we have a velocity now of 12.6 meters per second. Like we've done all throughout the year for a constant moving object, let's say there's no friction to really act on this baseball, we know this displacement here is the velocity times time, 12.6 meters per second, times the time from the beginning of the problem of 1.2. So we'll just take that velocity multiplied by a time of 1.2 seconds. We see our seconds go away, which is nice. And 12.6 times 1.2 gives us something around a displacement of 15 meters, which is about 45 feet. So this ball was kind of hit right back to the pitcher, maybe in between a little bit, maybe the third baseman's making a charge and then throw over to first, okay? Important takeaways from this problem are, in the beginning here, make sure that you are doing a conversion. Okay, make sure you know your conversions. Those are on the back of the best friend. 1 revolution equals 2 pi equals 360 degrees. And make sure you understand these kind of kinematic quantities that we have here, like a displacement equals a velocity times a time, or an angular displacement is an angular velocity times a time, and recognize that you might have to do some conversions as well between linear and angular, angular to linear, whichever way you're going. Other than that, and this problem is pretty straightforward because we didn't have an acceleration, so we basically have the easiest equations that we've used in the year. Okay? And with that, this problem is finished.